Exponentiation is a mathematical operation, written as Bn, involving two numbers, the base b and the exponent n. When n is a positive integer, exponentiation corresponds to repeated multiplication. In other words, a product of n factors, each of which is equal to b. Just as multiplication by a positive integer corresponds to repeated addition. The exponent is usually shown as a superscript to the right of the base. The exponentiation Bn can be read as b raised to the nth power, b raised to the power of n, or b raised by the exponent of n, most briefly as b to the n. Some exponents have their own pronunciation, for example, b2 is usually read as b squared and b3 as b cubed. The power Bn can be defined also when n is a negative integer, for non-zero b. No natural extension to all real b and n exists, but when the base b is a positive real number, Bn can be defined for all real and even complex exponents n via the exponential function is. Trigonometric functions can be expressed in terms of complex exponentiation. Exponentiation, where the exponent is a matrix, is used for solving systems of linear differential equations. Exponentiation is used pervasively in many other fields, including economics, biology, chemistry, physics, as well as computer science, with applications such as compound interest, population growth, chemical reaction kinetics, wave behavior, and public key cryptography. Background and terminology: the expression b2 equals bar b is called the square of b because the area of a square with side length b is b2. It is pronounced b squared. The expression b3 equals bar b is called the cube of b because the volume of a cube with side length b is b3. It is pronounced b cubed. The exponent says how many copies of the base are multiplied together. For example, 35 equals 3 a 3 a 3 a 3 a 3 equals 243. The base 3 appears 5 times in the repeated multiplication, because the exponent is 5. Here, 3 is the base, 5 is the exponent, and 243 is the power or, more specifically, the fifth power of 3, 3 raised to the fifth power, or 3 to the power of 5. The word raised is usually omitted, and very often power as well, so 35 is typically pronounced 3 to the fifth, or 3 to the 5. Exponentiation may be generalized from integer exponents to more general types of numbers. The word exponent was coined in 1544 by Michael Stifel. The modern notation for exponentiation was introduced by René copyright Descartes in his Gar copyright Omer copyright Try of 1637. Integer exponents: the exponentiation operation with integer exponents requires only elementary algebra. Positive integer exponents: formally, powers with positive integer exponents may be defined by the initial condition and the recurrence relation. From the associativity of multiplication, it follows that for any positive integers m and n, 0 exponent, any non-zero number raised by the exponent 0 is 1. One interpretation of such a power is as an empty product. The case of OO is discussed below. Negative exponents: the following identity holds for an arbitrary integer n and non-zero b. Raising 0 by a negative exponent is left undefined. The identity above may be derived through a definition aimed at extending the range of exponents to negative integers. For non-zero b and positive n, the recurrence relation from the previous subsection can be rewritten as. By defining this relation as valid for all integer n and non-zero b, it follows that, and more generally for any non-zero b and any non-negative integer n. This is then readily shown to be true for every integer n. Combinatorial interpretation: for non-negative integers n and m, the power nm equals the cardinality of the set of m tuples from an n-element set, or the number of m-letter words from an n-letter alphabet. Identities and properties: the following identities hold for all integer exponents, provided that the base is non-zero. Exponentiation is not commutative. This contrasts with addition and multiplication, which are. For example, 2 plus 3 equals 3 plus 2 equals 5 and 2 or 3 equals 3 or 2 equals 6, but 23 equals 8, whereas 32 equals 9. Exponentiation is not associative either. Addition and multiplication are. For example, plus 4 equals 2 plus equals 9 and a 4 equals 2 and equals 24, but 23 to the 4 is 84 or 4096, whereas 2 to the 34 is 281 or 2417851639229258349412352, 352. Without parentheses to modify the order of calculation, by convention the order is top-down, not bottom-up. Particular bases, powers of 10. In the base 10 number system, integer powers of 10 are written as the digit 1 followed or preceded by a number of zeros determined by the sign and magnitude of the exponent. For example, 103 equals 1010 or 4 equals 0.0001. Exponentiation with base 10 is used in scientific notation to denote large or small numbers. For instance, 299,792,458 AMS can be written as 2.9979245 A, 108 AMS and then approximated as 2.998 A, 108 AMS. SI prefixes based on powers of 10 are also used to describe small or large quantities. For example, the prefix kilo means 103 equals 1000, so a kilometer is 1000 meters. Powers of 2. The positive powers of 2 are important in computer science because there are 2n possible values for an n-bit binary register. Powers of 2 are important in set theory since a set with n members has a power set, or set of all subsets of the original set, with 2n members. The negative powers of 2 are commonly used, and the first two have special names, half, and quarter. In the base 2 number system, integer powers of 2 are written as 1 followed or preceded by a number of zeros determined by the sign and magnitude of the exponent. For example, 2 to the power of 3 is written as 1000 in binary. Powers of 1, the integer powers of 1 are all 1, 1n equals 1. Powers of 0, if the exponent is positive, the power of 0 is 0, 0n equals 0, where n greater than 0. If the exponent is negative, the power of 0 is undefined, because division by 0 is implied. If the exponent is 0, some authors define O equals 1, whereas others leave it undefined, as discussed below. Powers of -1, if n is an even integer, then equals 1. If n is an odd integer, then equals a 1. Because of this, powers of a 1 are useful for expressing alternating sequences. For a similar discussion of powers of the complex number I, see the section on powers of complex numbers. Large exponents, the limit of a sequence of powers of a number greater than 1 diverges, in other words they grow without bound, bnaa as naa when b greater than 1, this can be read as b to the power of n tends to plus or as n tends to infinity when b is greater than 1. Powers of a number with absolute value less than 1 tend to 0. Bn a 0 as naa when b1, any power of 1 is always itself, bn equals 1 for all n if b equals 1, if the number b varies tending to 1 as the exponent tends to infinity then the limit is not necessarily one of those above. A particularly important case is, 1 plus 1 slash n, nae is naa see the section below, the exponential function. Other limits, in particular of those tending to indeterminate forms, are described in limits of powers below. Rational exponents. An nth root of a number b is a number x such that xn equals b. If b is a positive real number and n is a positive integer, then there is exactly one positive real solution to xn equals b. This solution is called the principal nth root of b. It is denoted null shb, where a euro is the radical symbol. Alternatively, it may be written b1/n. For example, 41 halves equals 2, 81 thirds equals 2. This follows from noting that if n is even, then xn equals b has two real solutions if b is positive, which are the positive and negative nth roots. The equation has no solution in real numbers if b is negative. If n is odd, then xn equals b has one real solution. The solution is positive if b is positive and negative if b is negative. Rational powers mn, where mn is in lowest terms, are positive if m is even, negative for negative b if m and n are odd, and can be either sign if b is positive and n is even. 13 a equals a9, and 43/2 has two roots 8 and 8, however by convention 43/2 denotes the principal root which is 8. Since there is no real number x such that x2 equals a1, the definition of Bmn when b is negative and n is even must use the imaginary unit I, as described more fully in the section Powers of Complex Numbers. A power of a positive real number b with a rational exponent mn in lowest terms satisfies where m is an integer and n is a positive integer. Care needs to be taken when applying the power law identities with negative nth roots. For instance, a 27 equals a27, 22 equals a27, 22 equals a93 halves equals a27 is clearly wrong. The problem here occurs in taking the positive square root rather than the negative one at the last step, but in general the same sorts of problems occur as described for complex numbers in the section Failure of Power and Logarithm Identities. Real exponents. The identities and properties shown above for integer exponents are true for positive real numbers with non-integer exponents as well. However, the identity cannot be extended consistently to where b is a negative real number. See real exponents with negative bases. The failure of this identity is the basis for the problems with complex number powers detailed under Failure of Power and Logarithm Identities. The extension of exponentiation to real powers of positive real numbers can be done either by extending the rational powers to reals by continuity, or more usually as given in the section Powers via logarithms below. Limits of rational exponents. Since any irrational number can be approximated by a rational number, exponentiation of a positive real number b with an arbitrary real exponent x can be defined by continuity with the rule where the limit as a gets close to x is taken only over rational values of r. This limit only exists for positive b. The definition of limit is used. This involves showing that for any desired accuracy of the result one can choose a sufficiently small interval around x so all the rational powers in the interval are within the desired accuracy. For example, if the non-terminating decimal representation can be used to obtain the intervals bounded by rational powers, the bounded intervals converge to a unique real number, denoted by. This technique can be used to obtain any irrational power of b. The function is thus defined for any real number x. The exponential function. The important mathematical constant e, sometimes called Euler's number, is approximately equal to 2.718 and is the base of the natural logarithm. Although exponentiation of e could, in principle, be treated the same as exponentiation of any other real number, such exponentials turn out to have particularly elegant and useful properties. Among other things, these properties allow exponentials of e to be generalized in a natural way to other types of exponents, such as complex numbers or even matrices, while coinciding with the familiar meaning of exponentiation with rational exponents. As a consequence, the notation x usually denotes a generalized exponentiation definition called the exponential function, exp, x, which can be defined in many equivalent ways, for example by. Among other properties, exp satisfies the exponential identity. The exponential function is defined for all integer, fractional, real, and complex values of x. It can even be used to extend exponentiation to some non-numerical entities such as square matrices. Since is equal to e and satisfies the exponential identity, it immediately follows that exp, x, coincides with the repeated multiplication definition of x for integer x, and it also follows that rational powers denote roots as usual, so exp, x, coincides with the x definitions in the previous section for all real x by continuity. Powers via logarithms. The natural logarithm ln, x, is the inverse of the exponential function x. It is defined for b greater than 0, and satisfies. If bx is to preserve the logarithm and exponent rules, then one must have for each real number x. This can be used as an alternative definition of the real number power bx and agrees with the definition given above using rational exponents and continuity. the definition of exponentiation using logarithms is more common in the context of complex numbers, as discussed below. Real exponents with negative bases, powers of a positive real number, are always positive real numbers. The solution of x2 equals a4, however, can be either 2 or a 2. The principal value of 41/2 is 2, but a 2 is also a valid square root. If the definition of exponentiation of real numbers is extended to allow negative results, then the result is no longer well behaved. Neither the logarithm method nor the rational exponent method can be used to define b as a real number for a negative real number b and an arbitrary real number r. Indeed, r is positive for every real number r, so ln b is not defined as a real number for bar permel 0. The rational exponent method cannot be used for negative values of b because it relies on continuity. The function f, r, equals b has a unique continuous extension from the rational numbers to the real numbers for each b greater than 0. But when b less than 0, the function f is not even continuous on the set of rational numbers for which it is defined. For example, consider b equals a 1. The nth root of a 1 is a 1 for every odd natural number n. So if n is an odd positive integer, mn equals a 1 if m is odd, and mn equals 1 if m is even. Thus the set of rational numbers q for whichq equals 1 is dense in the rational numbers, as is the set of q for whichq equals a 1. This means that the function is not continuous at any rational number q where it is defined. On the other hand, arbitrary complex powers of negative numbers b can be defined by choosing a complex logarithm of b. Complex exponents with positive real bases, imaginary exponents with base e. The geometric interpretation of the operations on complex numbers and the definition of the exponential function is the clue to understanding ex for real x. Consider the right triangle. For big values of n, the triangle is almost a circular sector with a small central angle equal to xn radians. The trianglesque, k plus 1, are mutually similar for all values of k. So for large values of n, the limiting point OFN is the point on the unit circle whose angle from the positive real axis is x radians. The polar coordinates of this point are equals, and the Cartesian coordinates are. So Ex equals cos x plus is in x, and this is Euler's formula, connecting algebra to trigonometry by means of complex numbers. The solutions to the equation is equals 1 are the integer multiples of 2i. More generally, if f equals w, then every solution to is equals w can be obtained by adding an integer multiple of 2i to v. Thus the complex exponential function is a periodic function with period 2i. More simply, OE equals a 1. X plus I equals x, cos y plus I sin y. Trigonometric functions. It follows from Euler's formula stated above that the trigonometric functions cosine and sine are. Historically, cosine and sine were defined geometrically before the invention of complex numbers. The above formula reduces the complicated formulas for trigonometric functions of a sum into the simple exponentiation formula. Using exponentiation with complex exponents may reduce problems in trigonometry to algebra. Complex exponents with base e, the power z equals x plus I can be computed as x or y. The real factor x is the absolute value of z and the complex factor I identifies the direction of z. Complex exponents with positive real bases, if b is a positive real number, and z is any complex number, the power bz is defined as either ln, b, where x equals ln, b, is the unique real solution to the equation x equals b. So the same method working for real exponents also works for complex exponents. For example, 2i equals ln, 2, equals cos, ln, 2 plus eo sin, ln, 2 a permel 0.76924 plus 0.63896 I, a permel 0.54030 plus 0.84147 I, 10 ia permel 0.66820 plus 0.74398 I, E2 ia permel 535.49 ia permel 1, the identity is not generally valid. for complex powers. A simple counterexample is given by: the identity is, however, valid when as a real number, and also when as an integer. Powers of complex numbers. Integer powers of non-zero complex numbers are defined by repeated multiplication or division as above. If I is the imaginary unit and n is an integer, then n equals 1, I, a 1, or ai, according to whether the integer n is congruent to 0, 1, 2, or 3 modulo 4. Because of this, the powers of I are useful for expressing sequences of period 4. Complex powers of positive reals are defined via x as in section complex powers of positive real numbers above. These are continuous functions. Trying to extend these functions to the general case of non-integer powers of complex numbers that are not positive reals leads to difficulties. Either we define discontinuous functions or multi-valued functions. Neither of these options is entirely satisfactory. The rational power of a complex number must be the solution to an algebraic equation. Therefore it always has a finite number of possible values. For example, w equals z1/2 must be a solution to the equation w2 equals z. But if w is a solution, then so is aw, because 2 equals 1. A unique but somewhat arbitrary solution called the principal value can be chosen using a general rule which also applies for non-rational powers. Complex powers and logarithms are more naturally handled as single-valued functions on a Riemann surface. Single-valued versions are defined by choosing a sheet. The value has a discontinuity along a branch cut. Choosing one out of many solutions as the principal value leaves us with functions that are not continuous, and the usual rules for manipulating powers can lead us astray. Any non-rational power of a complex number has an infinite number of possible values because of the multi-valued nature of the complex logarithm. The principal value is a single value chosen from these by a rule which, amongst its other properties, ensures powers of complex numbers with a positive real part and zero imaginary part give the same value as for the corresponding real numbers. Exponentiating a real number to a complex power is formally a different operation from that for the corresponding complex number. However, in the common case of a positive real number the principal value is the same. The powers of negative real numbers are not always defined and are discontinuous even where defined. In fact, they are only defined when the exponent is a rational number with the denominator being an odd integer. When dealing with complex numbers the complex number operation is normally used instead. Complex exponents with complex bases, for complex numbers w and z with y permel a0, the notation wz is ambiguous in the same sense that log w is. To obtain a value of wz, first choose a logarithm of w. Call it log w. Such a choice may be the principal value log w, or perhaps a value given by some other branch of log w fixed in advance. Then, using the complex exponential function one defines. Because this agrees with the earlier definition in the case where w is a positive real number and the principal value of log w is used. If z is an integer, then the value of wz is independent of the choice of log w, and it agrees with the earlier definition of exponentation with an integer exponent. If z is a rational number mn in lowest terms with zar a0, then the infinitely many choices of log w yield only n different values for wz. These values are the n complex solutions S to the equation Sn equals Wm. If z is an irrational number, then the infinitely many choices of log w led to infinitely many distinct values for wz. The computation of complex powers is facilitated by converting the base w to polar form, as described in detail below. A similar construction is employed in quaternions. Complex roots of unity. A complex number w such that wn equals 1 for a positive integer n is an nth root of unity. Geometrically, the nth roots of unity lie on the unit circle of a complex plane at the vertices of a regular n-gon with one vertex on the real number 1. If wn equals 1 but wk a permel 1 for all natural numbers k such that 0, k, n, then w is called a primitive nth root of unity. The negative unit to 1 is the only primitive square root of unity. The imaginary unit I is one of the two primitive 40h roots of unity. The other one is ai. The number e2i is the primitive nth root of unity with the smallest positive complex argument. The other nth roots of unity are given by for 2 a per mole currency Ka per mole currency n. Roots of arbitrary complex numbers. Although there are infinitely many possible values for a general complex logarithm, there are only a finite number of values for the power wq in the important special case where q equals 1/n and n is a positive integer. These are the nth roots of w. They are solutions of the equation Zn equals w. As with real roots, a second root is also called a square root and a third root is also called a cube root. It is conventional in mathematics to define w1/n as the principal value of the root. If w is a positive real number, it is also conventional to select a positive real number as the principal value of the root w1/n. For general complex numbers, the nth root with the smallest argument is often selected as the principal value of the nth root operation, as with principal values of roots of unity. The set of nth roots of a complex number w is obtained by multiplying the principal value w1/n by each of the nth roots of unity. For example, the fourth roots of 16 are 2, a 2, 2i, and a 2i, because the principal value of the fourth root of 16 is 2 and the fourth roots of unity are 1, a 1, I, and ai. Computing complex powers. It is often easier to compute complex powers by writing the number to be exponentiated in polar form. Every complex number z can be written in the polar form, where r is a non-negative real number and I is the argument of z. The polar form has a simple geometric interpretation. If a complex number u plus iv is thought of as representing a point in the complex plane using Cartesian coordinates, then is the same point in polar coordinates. That is, r is the radius at u equals u2 plus v2 and I is the angle I equals at un2, v, u. The polar angle I is ambiguous since any integer multiple of 2i could be added to I without changing the location of the point. Each choice of I gives in general a different possible value of the power. A branch cut can be used to choose a specific value. The principal value corresponds to I chosen in the interval, I. For complex numbers with a positive real part and zero imaginary part, using the principal value gives the same result as using the corresponding real number. In order to compute the complex power Wz, write W in polar form. Then, and thus. If Z is decomposed as C plus D, then the formula for Wz can be written more explicitly as. This final formula allows complex powers to be computed easily from decompositions of the base into polar form and the exponent into Cartesian form. It is shown here both in polar form and in Cartesian form. The following examples used a principal value, the branch cut which causes I to be in the interval, I. To compute E, write I in polar and Cartesian forms. Then the formula above, with R equals 1, I equals I/2, C equals 0, and D equals 1, yields. Similarly, to find 3 plus 4i, compute the polar form of a 2. And use the formula above to compute. The value of a complex power depends on the branch used. For example, if the polar form I equals 1e5i/2 is used to compute II, the power is found to be a5i/2. The principal value of II, computed above, is ai/2. The set of all possible values for II is given by. So there is an infinity of values which are possible candidates for the value of E, one for each integer k. All of them have a zero imaginary part, so one can say E has an infinity of valid real values. Failure of power and logarithm identities. Some identities for powers and logarithms for positive real numbers will fail for complex numbers, no matter how complex powers and complex logarithms are defined as single-valued functions. For example, the identity log, bx, equals xa log b holds whenever b is a positive real number and x is a real number. But for the principal branch of a complex logarithm one has Regardless of which branch of the logarithm is used, a similar failure of the identity will exist. The best that can be said is that this identity does not hold even when considering log as a multi-valued function. The possible values of log, wz, contain those of za log euro w as a subset. Using log, w, for the principal value of log, w, and n as any integers, the possible values of both sides are the idemtitis equals bxcx and dx equals bxcx are valid when b and c are positive real numbers and x is a real number. But a calculation using principal branches shows that and. On the other hand, when x is an integer, the identities are valid for all non-zero complex numbers. If exponentiation is considered as a multi-valued function, then the possible values of 1/2 are 1, a1. The identity holds, but saying 1 equals a1, a1, 1/2 is wrong. The identity equals x holds for real numbers x and y, but assuming its truth for complex numbers leads to the following paradox, discovered in 1827 by Clausen: for any integer n, we have. But this is false when the integer n is non-zero. There are a number of problems in the reasoning. The major error is that changing the order of exponentiation and going from line 2 to 3 changes what the principal value chosen will be. From the multi-valued point of view, the first error occurs even sooner. Implicit in the first line is that e is a real number, whereas the result of e1 plus 2i euro n is a complex number better represented as e plus 0i. Substituting the complex number for the real on the second line makes the power have multiple possible values. Changing the order of exponentiation from lines 2 to 3 also affects how many possible values the result can have, but rather multi-valued over integers n. 0 to the power of 0, discrete exponents. There are many widely used formulas having terms involving natural number exponents, that require OO to be evaluated to 1. For example, regarding BO as an empty product assigns it the value 1, even when B equals 0. The combinatorial interpretation of OO is the number of empty tuples of elements from the empty set. There is exactly one empty tuple. Equivalently, the set-theoretic interpretation of OO is the number of functions from the empty set to the empty set. There is exactly one such function, the empty function. The definition of a van der Moen matrix assumes that OO equals 1. The notation for polynomials and power series relies on defining OO equals 1. Identities like and the binomial theorem are not valid for x equals 0 unless OO equals 1. In differential calculus, the power rule is not valid for n equals 1 at x equals 0 unless OO equals 1. However, not all sources define OO to be 1, particularly in the context of continuously varying exponents. Continuous exponents. When the form OO arises as a limit of, it must be handled as an indeterminate form. Limits involving algebraic operations can often be evaluated by replacing sub-expressions by their limits. If the resulting expression does not determine the original limit, the expression is known as an indeterminate form. In fact, when f, t, and g, t, are real-valued functions both approaching 0, with f, t, 0, the function f, t, g, t, need not approach 1. Depending on f and g, the limit of f, t, g, t, can be any non-negative real number or plus a, or it can be undefined. For example, the functions below are of the form f, t, g, t, with f, t, g, t, aaa0 as tar aa0 plus, but the limits are different. So OO is an indeterminate form. This behavior shows that the two-variable function xy, though continuous on the set, x, y, x greater than 0, cannot be extended to a continuous function on any set containing, no matter how OO is defined. However, under certain conditions, such as when f and g are both analytic functions and f is positive on the open interval for some positive b, the limit approaching from the right is always 1. In the complex domain, the function zw is defined for non-zero z by choosing a branch of log z and setting y equals e log z, but there is no branch of log z defined at z equals 0. let alone in a neighborhood of 0. History of differing points of view. The debate over the definition of OO has been going on at least since the early 19th century. At that time, most mathematicians agreed that OO equals 1, until in 1821 Cauchy listed OO along with expressions like 0/0 in a table of indeterminate forms. In the 1830s Libri published an unconvincing argument for OO equals 1, and Mar paragraph bias sided with him, erroneously claiming that whenever a commentator who signed his name simply as S provided the counterexample oft, and this quieted the debate for some time. More historical details can be found in Youth. More recent authors interpret the situation above in different ways. Some argue that the best value for OO depends on context, and hence that defining it once and for all is problematic. According to Benson, the choice whether to define OO is based on convenience, not on correctness. Others argue that OO should be defined as 1. Knuth contends strongly that OO has to be 1, drawing a distinction between the value OO, which should equal 1 as advocated by Libri, and the limiting form OO, which is necessarily an indeterminate form as listed by Cauchy. Both Cauchy and Libri were right, but Libri and his defenders did not understand why truth was on their side. Treatment on computers, IEEE floating point standard. The IEEE 754-2008 floating point standard is used in the design of most floating point libraries. It recommends a number of different functions for computing a power. Power treats OO as 1. This is the oldest defined version. If the power is an exact integer, the result is the same as for pound, otherwise the result is as for power. Pound treats OO as 1. The power must be an exact integer. The value is defined for negative bases. For example, pound, a 3, 5, is a 243, power treats OO as nan. The value is nan for for cases like power, a 3, 2, where the base is less than 0. The value is defined by e power a, log, base. Programming languages. Most programming language with a power function are implemented using the IEEE power function and therefore evaluate OO as 1. The later C and C++ standards describe this as the normative behavior. The Java standard mandates this behavior. The .NET Framework Method System MathPower also treats OO as 1. Mathematics software, Sage simplifies BO to 1, even if no constraints are placed on B. It takes OO to be 1, but does not simplify 0x for other x. Maple simplifies BO to 1 even if no constraints are placed on B, and evaluates OO to 1. Maple 16 simplifies 0x to 0. Maxima also simplifies BO to 1 even if no constraints are placed on B, but issues an error for OO. For x greater than 0, it simplifies 0x to 0. Mathematica and Wolfram Alpha simplify BO into 1, even if no constraints are placed on B. While Mathematica does not simplify 0x, Wolfram Alpha returns two results, 0 and indeterminate. Both Mathematica and Wolfram Alpha take OO to be an indeterminate form. MATLAB, Magma, GAP, Singular, PARIGP and the Google and iPhone calculators evaluate OO as 1. Limits of powers. The section 0 to the power of 0 gives a number of examples of limits which are of the indeterminate form OO. The limits in these examples exist, but have different values, showing that the two-variable function xy has no limit at the point. One may ask at what points this function does have a limit. More precisely, consider the function f, x, y, a equals axy defined on dar equals a, x, y, AAR2 AA ZAO A0. Then D can be viewed as a subset of A2 with x, y belonging to the extended real number line y equals a, AA, a plus a, endowed with a product topology, which will contain the points at which the function f has a limit. In fact, f has a limit at all accumulation points of D, except for and. Accordingly, this allows one to define the powers xy by continuity whenever 0 AA permel ZA permel plus a, AAA permel y permel plus a, except for 00, 0, 1 plus a and 1 AA, which remain indeterminate forms. Under this definition by continuity, we obtain x plus a equals plus a and ZA equals 0, when 1, x a per mil currency plus a. X plus a equals 0 when ZAR equals plus a, when 0 a per mil currency x less than 1. 0 y equals 0 and e equals plus a, when 0, y a per mil currency plus a. 0 y equals plus a and e equals 0, when a per mil currency y less than 0. These powers are obtained by taking limits of x y for positive values of x. This method does not permit a definition of xy when ZAR is 0, since pairs with ZAR 0 are not accumulation points of D. On the other hand, when n is an integer, the power xn is already meaningful for all values of x, including negative ones. This may make the definition 0 n equals a plus obtained above the negative n problematic when n is odd, since in this case xn a plus as x tends to 0 through positive values, but not negative ones. Efficient computation with integer exponents. The simplest method of computing Bn requires na1 multiplication operations, but it can be computed more efficiently than that, as illustrated by the following example. To compute 2100, note that 100 equals 64 plus 32 plus 4. Compute the following in order: 22 equals 4, 22, 2 equals 24 equals 16, 24, 2 equals 28 equals 256, 28, 2 equals 216 equals 65,536, 216, 2 equals 232 equals 4,294,967,296, 232, 2 equals 264 equals 184467440737095516116. 264 232 24 equals 2100 equals 12676500228229401496703205376. 703,205,376. This series of steps only requires 8 multiplication operations instead of 99. In general, the number of multiplication operations required to compute Bn can be reduced to I, log n, by using exponentiation by squaring or addition chain exponentiation. Finding the minimal sequence of multiplications for Bn is a difficult problem for which no efficient algorithms are currently known, but many reasonably efficient heuristic algorithms are available. Exponential notation for function names, placing an integer superscript after the name or symbol of a function, as if the function were being raised to a power, commonly refers to repeated function composition rather than repeated multiplication. Thus far3, x, may mean f, x. In particular, far1, x, usually denotes the inverse function of f. Iterated functions are of interest in the study of fractals and dynamical systems. Babbage was the first to study the problem of finding a functional square root far1/2, x. However, for historical reasons, a special syntax applies to the trigonometric functions. A positive exponent applied to the function's abbreviation means that the result is raised to that power, while an exponent of a 1 denotes the inverse function. That is, sin2x is just a shorthand way to write 2 without using parentheses, whereas sin1x refers to the inverse function of the sine, also called arcsin x. There is no need for a shorthand for the reciprocals of trigonometric functions since each has its own name and abbreviation. For example, 1/sin x equals a 1 equals cscax. A similar convention applies to logarithms, where log 2x usually means 2, not log x. Generalizations: in linear algebra AO is defined as I for every square matrix A, and n is the product. Moreover, if A is an invertible matrix, then AN is defined ASN. In abstract algebra, exponentiation for integer exponents can be defined for quite general structures in abstract algebra. Let X be a set with a power associative binary operation which is written multiplicatively. Then Xn is defined for any element x of X and any non-zero natural number n is the product of n copies of X, which is recursively defined by. One has the following properties. If the operation has a two-sided identity element 1, then XO is defined to be equal to 1 for any x. If the operation also has two-sided inverses, and multiplication is associative, then the magma is a group. The inverse of x can be denoted by ZAB1 and follows all the usual rules for exponents. If the multiplication operation is commutative, then the following holds. If the binary operation is written additively, as it often is for abelian groups, then exponentiation is repeated multiplication can be reinterpreted as multiplication is repeated addition. Thus, each of the laws of exponentiation above has an analog among laws of multiplication. When one has several operations around, any of which might be repeated using exponentiation, it is common to indicate which operation is being repeated by placing its symbol in the superscript. Thus, ZAB, n is xa, AAAA, x, while xn is xAAAX, whatever the operations a, and might be. Superscript notation is also used, especially in group theory, to indicate conjugation. That is, GH equals Ha1GH, where G and H are elements of some group. Although conjugation obeys some of the same laws as exponentiation, it is not an example of repeated multiplication in any sense. A quadral is an algebraic structure in which these laws of conjugation play a central role. Over sets. If n is a natural number and A is an arbitrary set, the expression n is often used to denote the set of ordered n tuples of elements of A. This is equivalent to letting n denote the set of functions from the set 0, A1, A2, AA euro, and R1 to the set A. The n tuple represents the function that sends I to I. For an infinite cardinal number I and a set A, the notation I is also used to denote the set of all functions from a set of size I to A. This is sometimes written IA to distinguish it from cardinal exponentiation, defined below. This generalized exponential can also be defined for operations on sets or for sets with extra structure. For example, in linear algebra, it makes sense to index direct sums of vector spaces over arbitrary index sets. That is, we can speak of where each phi is a vector space. Then if phi equals v for each I, the resulting direct sum can be written in exponential notation as VN, or simply Vn with the understanding that the direct sum is the default. We can again replace the set n with a cardinal number n to get Vn, although without choosing a specific standard set with cardinality n, this is defined only up to isomorphism. Taking V to be the field R of real numbers and n to be some natural number, we get the vector space that is most commonly studied in linear algebra, the Euclidean space Rn. If the base of the exponentiation operation is a set, the exponentiation operation is the Cartesian product unless otherwise stated. Since multiple Cartesian products produce an n-tuple, which can be represented by a function on a set of appropriate cardinality, Sn becomes simply the set of all functions from n to s in this case. This fits in with the exponentiation of cardinal numbers, in the sense that Sn equals Sn, where x is the cardinality of x. When 2 is defined as 0, 1, we have 2x equals 2x, where 2x, usually denoted by p, x, is the power set of x. Each subset y of x corresponds uniquely to a function on x taking the value 1 for za a y and 0 for za permilla y. In category theory. In a Cartesian closed category, the exponential operation can be used to raise an arbitrary object to the power of another object. This generalizes the Cartesian product in the category of sets. If 0 is an initial object in a Cartesian closed category, then the exponential object 00 is isomorphic to any terminal object 1. Of cardinal and ordinal numbers. In set theory, there are exponential operations for cardinal and ordinal numbers. If I and I are cardinal numbers, the expression II represents the cardinality of the set of functions from any set of cardinality I to any set of cardinality I. If I and I are finite, then this agrees with the ordinary arithmetic exponential operation. For example, the set of 3 tuples of elements from a 2-element set is cardinality 8 equals 23. In cardinal arithmetic, I0 is always 1. Exponentiation of cardinal numbers is distinct from exponentiation of ordinal numbers, which is defined by a limit process involving transfinite induction. Repeated exponentiation. Just as exponentiation of natural numbers is motivated by repeated multiplication, it is possible to define an operation based on repeated exponentiation. This operation is sometimes called titration. Iterating titration leads to another operation, and so on. This sequence of operations is expressed by the Ackermann function and Newton's up-arrow notation. Just as exponentiation grows faster than multiplication, which is faster growing than addition, titration is faster growing than exponentiation. Evaluated at the functions addition, multiplication, exponentiation, titration yields 6, 9, 27, and 7,625,597,484,987 respectively. In programming languages, the superscript notation XY is convenient in handwriting but inconvenient for typewriters and computer terminals that align the baselines of all characters on each line. Many programming languages have alternate ways of expressing exponentiation that do not use superscripts, XAY, ALGOL, Commodore BASIC, XY, BASIC, J, MATLAB, R, Microsoft Excel, TeX, TI BASIC, BC, Haskell, Lua, ASP and most computer algebra systems, XY, Haskell, D, XY, Ada, Bash, COBOL, CoffeeScript, Fortran, FoxPro, Knuplet, OCaml, F, Perl, PHP, PLI, Python, Regs, Ruby, SAS, Seed7, TCL, ABAP, Mercury, Haskell, Turing, VHDL, PoundXY, F, ZY, APL. Many programming languages lack syntactic support for exponentiation, but provide library functions. In Bash, C, C++, C, Java, JavaScript, Perl, PHP, Python and Ruby, the symbol represents bitewise XOR. In Pascal, it represents indirection. In OCaml and Standard Mill, it represents string concatenation. History of the notation. The term power was used by the Greek mathematician Euclid for the square of a line. Archimedes discovered and proved the law of exponents, 10 or 10 bar equals a 10a plus b, necessary to manipulate powers of 10. In the 9th century, the Persian mathematician Muhammad ibn Mazar al-Khwa used the terms mal for a square and kab for a cube, which later Islamic mathematicians represented in mathematical notation as m and k, respectively, by the 15th century, as seen in the work of Abu al-Hasan ibn Ala al-Khazidar. In the late 14th century, Jost bar 1/4 AGI used Roman numerals for exponents. Early 15th century. The first form of our modern exponential notation was used by René Descartes in his posthumous text not intended for publication entitled, Rules for the Direction of the Mind. It was based on the mathematical method and central to the elaboration of the Cartesian philosophy of science. The geometry depended directly on it. Rule 16 contains the first exponent in history, 2a3. Nicholas Chuckett used a form of exponential notation in the 15th century, which was later used by Henricus Grammateus and Michael Stifel in the 16th century. Samuel Jeake introduced the term indices in 1696. In the 16th century Robert Ricord used the term square, cube, zenzik, solid, zenzicube, seconds solid, and zenzik. The quadrate has been used to refer to the fourth power as well. Some mathematicians used exponents only for powers greater than 2, preferring to represent squares as repeated multiplication. Thus they would write polynomials, for example, as x plus bx x plus cx3 plus d. Another historical synonym, involution, is now rare and should not be confused with its more common meaning. List of whole number exponentials, see also, references. External links. SciMath FAQ, What is OO? Introducing zeroth power at planetmath.org. Laws of exponents with derivation and examples, What does 00 equal? On AskAMathmatician.com.